have on this smaller one. So those of you who don't know me, my name is Michael Helm, and I've been a ham operator since 1968. It works out to, what, 41 years now? Long time, since I was a kid. Been doing this for a long, long time. I love it. Haven't been real active in terms of talking on the radio recently, but I still like to build radio circuits. Anyway, I was asked to give a little talk on directional antennas today. So I brought you a few examples of ones that I've used on some of these rocket tracking events and balloon tracking events. And what I want to show you is how you can home make your own. I've never actually bought a commercial antenna of this type, ever. And having been a ham that many years, 40 years, I've never bought this kind of commercial antenna. I've always built this kind. And I bought commercial antennas for on my car. Mobile antennas for 2 meter and 440, and for the shortwave spectrum and HF band, I bought those kind of commercial antennas. But I don't actually have an example of the best antenna. The best ones I've got were made out of copper pipe and very heavy gauge copper wire, and they're mounted on towers at my house. I didn't have an example throwing around the workshop. These antennas I'm showing you here were built expressly for the balloon activities, trying to chase down payloads and keep track of payloads, and also the rockets. This one I threw together last spring in a very short evening in my workshop to track a 433 megahertz tracking transmitter on a rocket that the Esther Cutter Group took out to Las Cruces. And John Chandler saw to it that my way was paid to go out there. And so this gives some directivity in this direction. So if I've got a signal source off to the west here on this kind of an antenna, I can sweep it while I'm either listening to my radio or watching a meter on my radio for signal strength. I can sweep it. And if the corner up there of that wall, due west, I think it's due west, was where the source was, and if I swept this about this far off to the side, the signal would probably drop to about half strength on this particular antenna. And then as I swept it back the other direction, again it would drop about half strength when I got off at an angle about like that. And so what this allows me to do is by finding the two sort of half strength points, I can find the middle point where the strongest signal is. Now this kind of antenna doesn't directly work so well when you get real close to the transmitter. I thought about actually bringing a real weak signal transmitter tonight, but I thought, well, there's not really a good way to demonstrate it because when you get so close to the transmitter source, this antenna's got so much gain and your radios are so sensitive that the only way you can cut down the gain on the overall system is you have to use an attenuator between your antenna and the radio. And I've got one of those, but I was kind of doing some other stuff today and get a chance to pick it all up and bring it. But when you get real close with this kind of an antenna, what you can do is you can put that attenuator in there and put a whole lot of dBs of attenuation between the antenna and your radio, and then even though you're fairly close to the transmitter, the signal is attenuated so much it's still fairly weak and you still get this directivity. This one's been thrown around in the back of my Jeep for a while. That's one this old one's broken. Probably got a case of Dr. Pepper set on top of it or something. But anyway, if you want to figure out the gain of this antenna, it's related to the number of elements. So let's talk about this copper piece right here in the middle. This technique of impedance matching was developed by a friend of mine in the Dallas area, Ken Britton, WA5 BJB. He's been a ham about as long as me, maybe longer. And he's a really sharp guy. And he figured out this technique of matching this antenna with a, I don't know if you can see it, but it's sort of a J. We've got a loop here, and we've got a single element here on top. And it's something he developed. I don't know if he's absolutely the inventor of it, but I think he is. He wrote a really nice article in CQ magazine a few years back about it, and did several antenna design. This works real slick for impedance matching. I'm going to talk about some other techniques in a moment. But anyway, the simplest kind of antenna you can have is this single element called a driven element. And the simplest kind of antenna we typically would make would be just a dipole, a half-wave dipole. So this is cut for the 440 megahertz band, and the length from here to here is a half-wave length at that frequency. So there's formulas you can go figure that out easily enough. So the simplest antenna would be just this, what we call a director element, or a dipole by itself. If we want to make an antenna that's got a little bit of gain, we can put behind it, on the back side, what we call a reflector. Or alternatively, we can put in front of it, rather than back of it, a director. The difference between a reflector and a director is a reflector is a little bit longer than this driven element, and it tends to block signals in this direction from getting to the driven element. A director, on the other hand, is a little bit shorter, and it has the, without getting into a bunch of theory, just in a practical sense or intuitive sense how it works, as signals come in, they develop fields in these various elements and kind of focus the energy in on this driven element. And if you will go to a book such as the American Radio Relay League Radio Amateurs Handbook, ARL Handbook, you can buy those for about $35. The soft copy version, and well worth an investment if you are interested in this stuff. It's a very, very good resource about that thick. Some of you have seen them in my class. I've got them sitting on my desk. And they'll give you very specific formulas and all information about how to make one of these antennas really well. But even without looking at those formulas, you can, as a rough rule of thumb, you can set your director, set the reflector, a quarter wavelength behind it. In other words, half the length of this total distance here. Quarter wavelength back. Make the reflector 5% longer than this, which is cut to the frequency of interest. And then space all the elements a quarter wavelength. Make each one successfully about 5% shorter. Now you can make better antennas than that. There's equations, there's simulation software and what have you that will make a more precise antenna that performs a little better. But if you just want to do something quick and dirty, cheap, you can just throw the one together, and that's what I did. I just spaced these at quarter wavelength, 5% drop in length, 5% increase here, and use this little J-match techniques that Kent developed, and this works quite well enough. So, what about gain, and what about directivity of an antenna like this? Basically, if you've got the single driven element, that's a reference dipole. That's got a little bit gain more than an isotropic source, which is just a theoretical concept. So using the dipole as a reference point, if we put one element here, a reflector, that has the effect of giving us about 3 dB gain, which is effectively increasing the signal level by a factor of 2. And it makes the directivity of this about 90 degrees. So what that means is, if I'm aiming here west, and I've only got this reflector and I've only got the driven element, then I would have to turn this to a 90-degree angle to get the signal to drop off 3 dB, and drop off by half. Likewise, I'd have to turn it this way to get it to drop off by half. So that's not so good for pinpointing, although it would be better than nothing. To get another 3 dB gain, we've got to double the number of elements. So we'd have to go out here to 4 elements. That gives us, theoretically, a 6 dB gain antenna. And now, the points are approximately 45 degrees. So if I'm peaked here, 45 degrees over this way, it'll drop off by about half, and 45 degrees this way, it'll drop off by about half. This antenna, now to get another